Hello everyone, welcome to new class. Today's class is about time domain specifications. Let us find what are the time domain specifications. So, the desired performance characteristics of control systems are specified in terms of time domain specifications, and these can be specified in terms of the transient response to a unit step input signal. Transient response. So, the desired performance characteristics of a system of any order may be specified in terms of the transient response to unit step input, and the transient response of a practical control system often exhibit damped oscillation before reaching steady state. So, a typical damped oscillatory response of a system is shown in this figure, and the transient response characteristics of a control system to a unit step input is specified in terms of these time domain specifications. So, these are the time domain specifications: delay time TD, rise time TR, peak time TP, maximum overshoot MP, settling time TS. So, delay time TD. So, what is delay time? It is the time taken for response to reach 50% of the final value for the very first time. Then rise time TR. It is the time taken for response to rise from 0 to 100% for the very first time. And for underdamped system, the rise time is calculated from 0 to 100%. But for overdamped system, it is the time taken by the response to rise from 10% to 90%. And for critically damped system, it is the time taken for response to rise from 5% to 95%. Then TP, peak time. It is the time taken for the response to reach the peak value for the very first time, or it is the time taken for the response to reach the peak overshoot MP. Then what is peak overshoot MP? It is defined as the ratio of maximum peak value measured from the final value to the final value. Then settling time TS. It is defined as the time taken by the response to reach and stay within a specified error. And it is usually expressed as percentage of the final value. And the usual tolerable error is 2% or 5% of the final value. Let us take the expressions for the time domain specifications. First one is delay time, and it is the time taken for the response to reach 50% of the final value for the very first time. Then second one is rise time TR, and it is the time taken for the response to rise from 0 to 100% for the very first time. And for the underdamped system, the rise time is calculated from 0 to 100%. And for overdamped system, the rise time is taken by the response from 10% to 90%. And for critically damped system, the time taken for the response to rise from 5% to 95% is taken. And to find the expression for the rise time Tr, we have the response of the second order system. C of t is equal to 1 minus e raised to minus zeta omega nt divided by root of 1 minus zeta square sine omega dt plus theta. And the rise time is obtained when this response is equal to 1. That is, at t equal to tr, c of tr equal to 1. So, by equating this equation to 1 and after solving this tr, we get the rise time tr is equal to pi minus theta divided by omega d, where theta is tan inverse of root of 1 minus theta square divided by theta, and omega d is the damped frequency of oscillation and is equal to omega n into root of 1 minus theta square. Next is peak time Tp. It is the time taken for the response to reach the peak value for the very first time, or it is the time taken for the response to reach the peak overshoot Mp. And it is obtained by differentiating the response to T and equate it to 0. So, after differentiating and equating to 0, we get a Tp. The peak time Tp equal to pi divided by omega d and is equal to pi divided by omega d is omega n into square root of 1 minus theta square. Next is peak overshoot Mp. It is the ratio of the maximum peak value measured from final value to the final value. And let final value be C of infinity, then maximum value be C of Tp. Then we have peak overshoot Mp is equal to C of Tp minus C of infinity divided by C of infinity, and it is expressed in percentage. So percentage peak overshoot Mp is equal to C of Tp minus C of infinity divided by C of infinity into 100. And it is obtained from this expression, and we have the response C of t is equal to 1 minus e raised to minus theta omega nt divided by square root of 1 minus theta square into sine omega d t plus theta. And after substituting C of Tp and C, after finding C of Tp here and C of infinity and solving, we get a percentage peak overshoot, that is percentage Mp is equal to 1 plus e raised to minus theta pi divided by root of 1 minus theta square. That is, we get C of Tp as e raised to minus theta pi divided by root of 1 minus theta square and C of infinity as 1. So after substituting this, we get peak overshoot. That is, percentage peak overshoot is equal to e raised to minus theta pi divided by square root of 1 minus theta square into 100. Next is settling time Ts. It is the time taken by the response to reach and stay within a specified error. It is usually expressed as percentage of final value. The usual tolerable error is 2% or 5% of the final value. And we have the response of the second order system. C of t is equal to 1 minus e raised to minus theta omega nt divided by square root of 1 minus theta square into sine omega dt plus theta. So this response has two components. One is decaying exponential component, this one e raised to minus theta omega nt divided by square root of 1 minus theta square, and the second one is sinusoidal component sine of omega dt plus theta. And in this, the decaying exponential term reduces the oscillations produced by the sinusoidal component. Hence, the settling time is decided by the exponential component. So, the settling time can be found out by equating the exponential component to percentage error, that is percentage tolerance errors. First of all, equate this e raised to minus eta omega nt divided by square root of 1 minus eta square to 2% error. Then we get this, and after equating to 5% error we get this. And for least values of theta, we equate only the numerator. So equate the numerator term to 2% error. Then the settling time obtained is 4 divided by zeta omega n, or we can write 4 into t, where t is the time constant and is equal to 1 divided by zeta omega n. And by equating this numerator term, that is e raised to minus zeta omega nt to 5% error, we get 3 divided by zeta omega n, and that is equal to 3t. Or in general, for a specified percentage error, we can write the settling time Ts is equal to Ln, that is the natural logarithm of percentage error divided by zeta omega n. So if 2% error, we can write 2%, or Ln, that is natural logarithm of 0.02, or in case of 5% error, Ln 0.05. So this is about the time domain specifications and their expressions. So thank you for watching the class. If you like the classes, please like, share and subscribe my channel.